Recursive 3-n magic squares, prime structures, and future applications. Read 3-n as 3 to the n. This project begins with a simple object, the magic square. A magic square is a square grid of numbers in which every row, every column, and the two main diagonals add to the same total. At first glance, that may sound like a mathematical curiosity, something decorative or recreational. But once the square is studied structurally, it becomes much more interesting. A magic square is not merely a grid with equal sums. It is a balancing system. Each number has a position. Each position has a role. The center controls the symmetry. Opposite positions are connected. Rows, columns, and diagonals are not isolated lines. They are parts of one coordinated whole. The most important starting point is the 3x3 magic square. In a 3-3 square, all structure is governed by the center. Around that center, the 8 surrounding positions can be understood as balanced pairs. If the center is called C, then the surrounding entries can be written as values above and below C by certain displacements. In plain language, the square is built from a center and a shell. That shell is not random. It is a precise balancing pattern. Every row, column, and diagonal sums to 3 times the center. This makes the 3x3 square the primitive unit of the whole framework. It is the first small machine. The next step is recursion. A 3-n magic square is a magic square whose side length is a power of 3. 3, 9, 27, 81, 2 and 43, 7, 29, and so on. These sizes matter because each larger square can be viewed as being made from smaller 3x3 structures. A 9x9 square can be viewed as a 3x3 arrangement of 3x3 blocks. A 27x27 square can be viewed as a 3x3 arrangement of 9x9 blocks, or as a 9x9 arrangement of 3x3 blocks. An 81x81 square continues this pattern, and so does every high power of 3. This is where the structure becomes genuinely recursive. The square is not just larger, it is layered. A cell belongs to a small 3x3 block. That block belongs to a 9x9 block. That 9x9 block belongs to a 27x27 block. The same balancing logic repeats across scale. The local structure and the global structure are connected. This means a properly nested 3n magic square is not only one magic square, it contains smaller aligned magic squares inside itself. The full object becomes a hierarchy of balanced regions. This is important because it gives us a way to think about complexity without losing control of it. Instead of treating a large square as thousands or millions of unrelated entries, we treat it as a recursive system. Center, shell, block, parent block, higher block, full square. That is the basic mathematical architecture. Now the project becomes more demanding. Instead of using ordinary consecutive numbers, the goal is to build these recursive magic square structures from prime numbers. Prime numbers are numbers greater than 1 that cannot be divided cleanly except by 1 and themselves. They are simple to define but difficult to control. They do not appear in neat, evenly spaced order. They thin out as numbers get larger. They obey modular restrictions. They create gaps, clusters, and irregular patterns. So asking primes to form a magic square is already difficult. Asking distinct primes to form a recursively nested 3-n magic square is much harder. Each entry must be prime. Each entry must be unique. Each local 3x3 shell must balance. Each larger block must balance. The rows, columns, and diagonals must balance. And the same prime cannot be reused somewhere else simply because it is convenient. This changes the problem completely. We are no longer merely arranging primes. We are filtering primes through a recursive balancing structure. A prime is not useful just because it is prime. It must be able to cooperate with other primes around a center. For a 3x3 prime shell, the center must support symmetric prime pairs around it. If C is the center, then values like C plus A and C minus A must both be prime. The same must happen for several related displacements. The shell only works when all these prime pairs close together at the same time. This leads to the idea of prime shell fertility. A prime center is fertile when it has many possible prime shells around it. It is not fertile when it is prime, but cannot support the surrounding structure. This distinction is crucial. In ordinary number theory, a prime is often treated as an individual object. In this framework, a prime is judged by its ability to participate in a balanced recursive system. That is one of the central ideas of the work. The magic square acts like a sieve. It does not merely ask whether numbers are prime, it asks whether primes can coordinate. Certain modular patterns also become important. Since primes greater than 5 cannot be divisible by 2, 3, or 5, they must occupy certain residue classes modulo 30. In simple terms, they can only live in certain lanes. When primes are placed symmetrically around a centre, the displacement between the centre and the outer values must also respect these lanes. So the construction is governed by several layers at once: the centre shell pattern, the recursive 3-gen block hierarchy, prime pair symmetry, modular admissibility, global uniqueness, and verification at every nested scale. This is why the result is not just a large table of primes. It is a structured object. The significance of finding 3-gen structures in the prime number realm is not that it proves a hidden law of primes. That would be too strong. The responsible claim is more careful. The significance is that primes, despite their irregularity, can be organized into highly constrained recursive structures. They can be made to obey local and global balancing rules at the same time. This suggests that there are useful ways of studying primes not only by their individual distribution, but by their ability to participate in structured systems. That is a different lens. Instead of asking only, where are the primes, we can also ask, which primes can cooperate under a recursive constraint? This matters because many difficult systems behave in this way. The important objects are not just individual parts, but parts that remain compatible under many simultaneous rules. A recursive prime magic square is therefore both a mathematical construction and a test environment. It tests how local choices survive global constraints. It tests how abundance becomes scarcity once structure is imposed. It tests how symmetry, residue, uniqueness, and recursion interact. This is also why failure is informative. When a construction fails, it may not fail because there are not enough primes. It may fail because a centre is not fertile enough, or because a local shell cannot close, or because two distant regions need the same prime, or because a residue lane becomes crowded because a locally good choice destroys future options. That is not wasted information. It tells us where the structure is under pressure. This moves the project from simple construction into method. The method is to build recursively, verify brutally, and distinguish different kinds of failure. A partial structure is not called solved. A scaffold is not called globally unique. A local success is not treated as a global proof. The square must earn every claim made about it. That discipline matters because the future applications are only meaningful if the mathematical language remains honest. The next conceptual bridge is to compare 3-then magic square structures with Latin squares. A Latin square is a grid in which each symbol appears exactly once in every row and once in every column. Latin squares are excellent at controlled placement. They ensure that labels or states are distributed evenly. Magic squares do something different. They control balance. They make sums, centers, and oppositions matter. So, Latin squares are about distribution. Magic squares are about conservation. The future direction is to study how these two structures can be correlated. A Latin square can organize symbols, labels, phases, categories, or states. A magic square can organize weighted balance, total conservation, recursive correction, and multi-scale structure. A hybrid system could therefore combine clean symbolic placement with arithmetic or energetic balance. That is where the idea becomes useful beyond pure number construction. In quantum computing, one of the major challenges is not simply storing information, but controlling relationships between states. Quantum systems involve phases, bases, transformations, interference, and error correction. Latin square-like structures already have natural relevance to organized state placement and combinatorial design. Magic square-like structures may add another layer: balanced relationships, recursive local-to-global correction, and structured defect tracking. The cautious future claim is not that recursive magic squares solve quantum computing. They do not. The useful claim is that recursive 3-then structures may provide a language for organizing constraints in systems where local states must remain globally coherent. A similar idea appears in solar energy systems. Solar panels are often arranged in arrays. When part of an array is shaded, the problem is not only that one panel performs badly. The shading can create imbalance across the whole system. Rearranging how modules are connected or organized can spread the stress more evenly. Latin square and magic square inspired layouts are relevant here because they offer ways to distribute local disturbance across a larger structure. Again, the claim is not that a prime magic square directly improves a solar panel. The claim is that the same family of ideas, structured distribution, balance constraint, recursive compensation, may help design better arrangement and control strategies. That distinction matters. The mathematical object is not the application. The mathematical object is the grammar. Once the grammar is understood, it can be tested in different fields. In signal processing, a recursive magic square framework could help separate local noise from global pattern. In optimization, it could help manage candidate selection under many constraints. In AI-assisted research, it can act as a discipline for avoiding uncontrolled speculation. Define the structure, generate candidates, test them, classify failures, and never confuse a beautiful pattern with a verified result. For specialist readers, the deeper direction is this. 3n magic square structures may be treated as recursive constraint systems. Their cells are not passive positions. Each cell has a role determined by its scale, block membership, opposite partner, line family, center relation, residue class, and future expansion obligation. Prime constructions then become a form of constrained lifting. An ordinary recursive skeleton is projected into the prime number realm through residue filters, prime pair fertility, shell closure, and global uniqueness. That language may sound technical, but the underlying idea is simple. A number is not merely placed into a square, it enters a role, and the role must remain compatible across scale. And this is why the project is concerned with 3-thren structures rather than arbitrary square sizes. Powers of 3 allow the 3x3 center shell grammar to repeat cleanly. They allow local balance to become block balance, and block balance to become global balance. The long-term research direction is to understand how far this recursive grammar can be pushed, what its limits are, and where similar structures appear in other mathematical or physical systems. The current work should therefore be read humbly but firmly. It is not a proof of an infinite family. It is not a claim that primes secretly behave like magic squares. It is not a claim that quantum computers or solar panels can be redesigned from this alone. It is a verified construction program and a developing framework. It shows that distinct primes can be organized inside recursive 3n magic square structures. It shows that the construction depends on more than primality. It depends on centers, shells, residues, fertility, uniqueness, and recursive verification. It suggests that these structures may have value as models of constrained coordination. That is the central point. The square is not just a square, it is a compact way of studying how local order survives global pressure. And in many serious fields, from mathematics to computation to energy systems, that is exactly the kind of problem that matters.